Okay, Erlang, open networking, and the future of computing. Who here has heard of the open networking movement? Okay. Who here likes Erlang? Okay. Who here is interested in the future of computing? It's a crowd pleaser. Okay. So it is a broad talk, but that's okay. I hope to hit on major themes that should interest at least some of you. But my goal is really to excite the whole community, Erlang community, about opportunities that really are right in front of us. And I got to tell you, for me, I'm the founder and CTO of Infoblox. If you've not heard of us, I'm not surprised. We're a company that does network control and automation, primarily for bigger companies. We've been around for 14 years. We're a public company now, and it's pretty industrial. So if you haven't heard of us, I'm not surprised at all. So it really begs the question of why I'm here. And if you figure that out, let me know, because others back at home want to know that too. And one answer is Stockholm in summer. This is pretty nice. I really have fallen in love with Stockholm, and I'm sure I'll be back, but probably not in the winter. That's my goal, to avoid that. And I really am very, very excited to be here at Erlang. This is at the Erlang Users Conference. It's my first Erlang Users Conference. So is Katie in the audience? Okay, so from our keynote from yesterday, I am a relative newcomer. I heard about Erlang for the first time in 2006, and this is the very first time I've actually been at the Erlang User Conference itself. It's an amazing place already, right? This is, I think, the only conference where I can hear about Erlang in the context of a movement and see internet cats, right, in our keynote yesterday, and then go to a talk about distributed computing from Matthias, I think that's how you pronounce your name, and hear an in-depth analysis of the Battle of Stalingrad in World War II. That's amazing. It's an amazing juxtaposition there. And I think it's representative, actually. I think it's representative of the kinds of currents in technology that are really mixing around the Erlang community today. And that's, I hopefully by the end of this talk, you'll have some idea about why I'm here. Why would I, other than being an Erlang enthusiast, which I am, what attracted me to this conference today? And I think what got me here is something that's going on fundamentally in the industry, which I hope the Erlang community at large can embrace. So, to start with, I'm a CTO. The T, I think, stands for talking, Chief Talking Officer. One of my job functions is, however, to ask questions, so I have some idea of what I should probably be talking about. So I'm going to go through 3 questions that have come up in the course of our business. And I think these are 3 questions that I've heard resonate through the different talks I sat through yesterday and the talks I see on the track today, but you'll have to tell me at the end of the day. The first, these are networking questions. The first question in our business is, what is the business view of the network? That's a problem that we have as a business, to try to find that out. And, I think if any of you have been around kind of large-scale enterprise networks or telecommunication networks, it's actually pretty disconnected from the business processes in general, right? So one question is there some view of the network that is somehow more attached to the business? So that's like a business question. And that's a question you might not have, but I have to answer because of the business we happen to be in. Now, another question which seems maybe a little broader and relates, again, to our business, but I think is at least a little bit broader, which is how do we actually program? What is this Internet of Things, and how do we program it? Right. So if the Internet of Things is about lots of things, maybe sensors in healthcare that are on, your family members in healthcare situations that have to get data to the right place at the right time, otherwise the right kind of healthcare isn't going to be provided, or optimization for oil and gas, digital oil fields, across all these industries, retail, optimizing the store shelves. These are distributed applications. The question isn't how do I connect all these things, but really how do I program a collection of these things to do something fundamental to the organization. And so I would even challenge whether this is really what we're talking about as an Internet of Things at all, right? It's really an interactive network of things. And I didn't coin that term. IDC coined that term in a report that they put out at Interop 2012, I believe, or 2013, where they said they think 20 billion devices will be connected by 2020. So I have this fundamental question: how can we program this thing? And then it's actually related, and maybe of interest to several of you. How do we program a million cores? So I had the privilege yesterday to see Richard Croucher's talk called Go Big. One of the great things about this series of conferences is that you can watch all the talks, I believe, on video shortly after the conference. If you're interested in this problem, I recommend that you watch Richard's talk, because it really goes into kind of the history of high-performance computing and how we've thought about these things, kind of historically. And here's somebody. Richard, are you in the audience? Yeah. Okay. So Richard, has a very long and deep experience solving problems of distributed computing at scale, and he's here. Why is he here? Why am I here? I mean, again, I don't think it's just because of the weather, right? There seems to be maybe something fundamental here that's starting to attract certain people interested in these kinds of questions in general. Now, when you have that kind of scale, right, there's a funny thing, right? In all of these questions, there's this underlying assumption now that you just have a lot of stuff, so statistically, stuff's just failing. So in the enterprise case, stuff may be being replaced a lot. It might not actually be failing. It may be very dynamic. You have cloud workloads and mobile workloads. In the Internet of Things, again, dynamism, but also stuff just, doesn't work as much. So how do we, somewhere I heard this term, maybe it's Joe's term, I think it is, write once, run forever, right? I think that's this kind of nonstop. So how do we do this? And again, respectful to, I think Katie's message yesterday was really, really important, which is to answer these questions. Many of you sitting in chairs today absolutely already know the answer, right? Of course, Erlang. Of course. What other system even comes close to having the properties, unless you built it somehow by hand or with a lot of people? But for kind of any 1, 5, 10 of you to think about fundamentally being able to program an Internet of Things, program a million cores, or find out very deeply what's happening on a large network, I don't know of any other system that comes close. But not everyone knows that. That is still the Erlang community's secret. I encourage you to embrace Katie's message and, double this room next year, right? And work on some of the hard problems. Now, there's a subtle problem. Again, I almost want to just have Richard come up and give his talk. It's just a great talk because he really articulated my experience, which is this kind of hype cycle on Erlang, right? I've had a long time doing distributed systems, and when I got first exposed, and in fact, if I had been exposed to Erlang before starting Infoblocks, it's very likely that our core technologies would be based on Erlang. They're not. I was exposed to Erlang in 2006. None of the things I'm going to talk to you about here have to do with our core technology that we sell today. Maybe that'll change. I hope it will. Kind of depends on you. But I had this visceral experience, which is I had a set of problems in my mind that as an organization we had solved at some degree for the kinds of things we're trying to do. And when I got exposed to Erlang in 2006, I just said, wow, this has the right properties. Man, I just wish and I really started to get over that learning curve on the language, and I had been, only briefly exposed to functional programming, so I had to do all that stuff, read Joe's book. And time again, I was like, well, I'm sure that they've done this. And then it wasn't quite there. Or I'm sure that, it'll scale to 1,000 nodes, right? That should be, it's like 2006, right? 30 nodes, 100 nodes, that's like 1996. It's 2006, 10 years later. I'm sure they've gotten an order of magnitude more, but no. And so that's okay. But over and over again, this idea of the network keeps coming up, and we saw it in talks yesterday as well. So my team's first reaction, and my first reaction, having a high-performance computing background was, well, there's always an answer to networking problems when you have lots and lots of things, especially if they're relatively close together, and that's InfiniBand, right? And if you're not familiar with this, that basically says eventually for distributed applications where they have to collaborate, you have to take out TCP/IP. And so maybe it's InfiniBand, maybe it's MirrorNet, maybe it's a host of other technologies, but there's a problem, which is unless you're doing HPC, which has a very high-performance computing, which is a very kind of special shape as an industry. It grows about 3% a year, and tremendous amounts of dollars are put to a few number of solutions. So it has this kind of it's pretty expensive. Now, it doesn't mean that it's necessarily expensive today because prices are going down, but kind of overall, it's hard to find people who understand how to do this. But something tremendous has happened in the last 20 years, and that's Ethernet. So the story of networking over the last 20 years is not the internet. That's very exciting, no question about it. We wouldn't be here. But there's this other story that Ethernet won. 90% of the ports that Cisco ship are Ethernet, right? It's everywhere. Who knows what a Raspberry Pi is? Yeah, wow, that's awesome. See, that's why I like coming to the Erlang user conference, because most groups, when I ask that in the circles I tend to be in, don't know yet what this is. But right, 100 meg Ethernet, it's just everywhere. And so one way to view the world, if you think about those pictures, is the world is today already installed an Ethernet fabric. And that's something that I think this community can leverage tremendously. But the network today is structured with little boxes that do things. And I don't know about you, but if you've been doing Erlang or distributed systems, somewhere along the line you start thinking about your distributed app, and then there's this network. And then you have to get the network people, you have to learn about networking. So if you're in the audience and you don't know anything about networking, and you have a sense, though, that you're trying to do distributed computing, so maybe you should know about networking, this is an amazing time in history, and maybe one thing you'll take away from this talk is you actually don't need to know much about the way we've been doing networking. There's an opportunity to do networking in a different way going forward. The way we have been doing it is that we have these dedicated function boxes. Firewalls, routers, load balancers, other dedicated functions, and there are specialists in all those, and we put those together, and that's how we think about the network, and somehow that's underneath these big scalable distributed systems, and there's kind of an impedance mismatch there. There's kind of a tension there. There's a tension there culturally sometimes. in the networking community versus the kind of computing community, and then it's even broader in the distributed computing community versus the networking community. So imagine, if you will, instead of those dedicated functions with specific protocols, you actually had a programmable fabric. Who here's heard of OpenFlow? Wow, I love it. Okay, yeah, so that's good. So one way to think about OpenFlow is if all of those dedicated function boxes became programmable Ethernet junctions, meaning just places where if there's a flow, does this have a, yeah, a flow here going through all these boxes. This is maybe a cell phone here and a data center here. This is a sensor here and some other sensor there that are collaborating or somehow calibrating themselves somehow, for instance. That this is just a bunch of Ethernet ports and then a CPU, NPU, something that's programmable. This is the same thing, this is the same thing. And then from somewhere else remotely, this could be in the cloud, something like that, you can actually program each one of these junctions to inspect the packets, load balance, firewall, route, do something else, without any preconceived notion about what those things mean. And most importantly, they could be those functions can be controlled by the application themselves. So you can really have a network that's really exactly the way you want it. If you're a distributed application developer, you can have a network exactly the way you want it. And then in that kind of light, OpenFlow looks like an instruction set for remotely programming Ethernet. So that's a very interesting model. And this is what sparked my attention, circa about 2011, I'm sorry. And I got very involved in the organization that owns this particular standard, which is the Open Networking Foundation, which is driven by Google, Facebook, Deutsche Telekom, I believe, Microsoft Azure. So folks like Richard who really viscerally understand what the network is going to need in terms of responsiveness to distributed applications. I have no idea whether OpenFlow is going to be successful in the long run, but I'm quite convinced that this model has tremendous merit. And that's what I'm going to talk to you about is our kind of exploration into this model. I'm not making any claims. If you take one thing away is this is the time to deeply investigate this model and whether it's appropriate. Maybe it is, maybe it isn't. No one actually knows. If you know and have proof, see me after the talk, right? But I've talked to just about everybody I can find who has a message or a story about programmable networks, software-defined networks, high-density data center, dynamic networks, and I can tell you no one knows exactly, but pretty much everybody agrees that that old hardware-defined network model is not sustainable in a growing class of applications. Doesn't mean it's going to take over everything, but it's not sustainable. It's very similar. Some people think, well, hey, isn't this like virtualization in the computing world? But really, no. Virtualization, the introduction of the hypervisor into a mass market, had two kind of things that had to happen first. The x86 had to become a ubiquitous microprocessor platform, be installed everywhere, like Ethernet's installed everywhere. And there had to be an independent software market in computing. And then you had something like the hypervisor. This looks a lot more like the transition of hardware-focused computing in the 70s to software-focused computing in the 80s and beyond. In the networking industry, the structure of the networking industry, not the technology, the structure of the industry, it's all organized around hardware. So it's tremendously disruptive to the whole industry. In the same way, kind of the electric car like Tesla with 36 moving parts, right, is disrupted, it's like an iPad on wheels, right, is disruptive to the whole industry structure of the automotive industry. Because you don't, with 36 moving parts, you don't need the same number of mechanics, right? If the car's not organized around the combustion engine, the entire industry structure is affected by that. So that's what's happening here. So why is that important to you? Well, maybe there'll be a sense of that by the end of the talk, but just know this community is very, very, has a right, actually, for lots of historical reasons, to participate in that disruption fundamentally because of the history of Erlang as a telecommunications platform, which is just kind of amazing and crazy. So if you want to learn more about this kind of stuff and participate, we have been doing an open source community for a couple years now called flowforwarding.org. Check it out. I'm going to highlight some of the things that we're talking about there in this talk, but come and participate. That's the main thing. Oops. So what have we been doing at flowforwarding.org? So first of all, we said, okay, all this stuff's happening. I'm the chief talking officer, right? It should be my responsibility to understand whether all this software-defined networking, programmable network is a fraud, a fad, or fundamental. And so the project at flowforwarding.org was all about trying to answer that question. Could we build up the technology from the ground without, in a kind of clean room situation so we could understand viscerally whether there's something fundamental going on or whether there's this kind of noise in the marketplace? It is my conviction today that there's something absolutely fundamental going on. And that's quite exciting. We actually, I'm probably the worst Erlang programmer in the room. So it would be bad if I was the person to do the actual stuff. I think, mess around a little bit. But we hired Erlang Solutions, Cloud Dozer, EPAM, and we have a growing, so if you're into programming Erlang, we think we have a whole host of problems that we're interested in and that we think the community at large is interested in. We started with Erlang Solutions to develop a switch, one of these programmable data planes in software to run on CPUs. We call it Link. Then we released a kind of proof of concept of what's a control plane, that blue thing, and an actual sample application. Then we hired Cloud Dozer, and we'll hear about that in a little bit, to make Link even faster on commodity CPUs, so we could understand whether with a CPU could you actually inspect every single Ethernet frame, right? And we're giving it all away for free. This is not something we're trying to monetize, because our interest is in answering the fundamental questions. Is this something going on that's going to affect the whole industry? So it's a really great place to participate. So, is it any good? I don't know. But it would be great if you tried it out, made it better, so in the end of the day, I can say this was really worthwhile. Because I'll tell you, I do get a lot of flack, especially in the networking community, which I think is somewhat ironic. But I do get a lot of flack for embracing Erlang. So you can help me with that. I would be very appreciative if at the end of the day this was super successful, largely because you made it so. Okay, so one thing that instead of kind of starting at the bottom and figuring out, okay, here are the kind of bits and bytes, and then immediately getting into arguments like, well, can you drive gigi? Can you drive 10 gigi? Can you do this? Can you do that? What about small packets versus big packets, right? It's very much like in the computing industry, talking about LinPack and other thing. We wanted to make an application that somehow didn't do necessarily anything really important, but that it touched on all three major themes. Programmability and visibility into enterprise networks, big data, a big data problem that might require 1 million cores eventually to solve, right? And an Internet of Things, very widely distributed network devices. So the way to think about Tapestry is, who here are Haskell people? Haskell? Okay. So I heard, so this is Haskell talking, not me. I can't remember who exactly it was, said, Haskell, because of its very narrow focus on the Turing machine and exploring that, was kind of, designed to be relatively worthless, but, explored this one kind of thing very deeply. And so Tapestry is kind of like that, right? I'm not claiming that there's any huge value in this, but I think it touches on all three major themes. So it's worthwhile investigating. And so it touches on SDN, big data, and IoT, Internet of Things all at once. That seems like a big claim. Any of these claims, you should just download the code and try it, and then you'd be like, that's crazy. But I think this highlights what we're trying to do here, which is it has the data path element, which is the switches, the things that actually touch the packets, inspect it, Ethernet packets. Control plane, which imagine if you had, 10,000 programmable Ethernet processors and you needed to control them to do different things with flows of Ethernet, that's what the control plane does. We call it Loom. This is called Link. And then this application, which is a network telemetry application that gathers telemetry from all of these switches while these switches are processing normal enterprise traffic, collects it, and then computes a number. This is a big data computational problem up here. So I'll talk a little bit about that. But the output here is that we have an entire stack, right? That has a big data component, a software-defined networking component, and an entire stack, 100% in Erlang. 100%. You can write this whole thing on x86 boxes, so every single part of the stack is on Erlang. And it doesn't have to be all put together if you don't want to. I'm actually leaving the conference after this talk, unfortunately, because I would really like to stay here. Next year, I'd like to stay longer. And I'm going to Tokyo, where we're running Tapestry, which is the big data component, in the Tokyo Interop show floor. And in that case, we're not actually using these switches. We actually get the data to do the computation from a different source. But it's a big data, so it also needs kind of SDN properties in the middle. So you can kind of pick and choose these layers, or you can use them all at once. And we've deployed the whole stack, for instance, internally at Infoblox. And it's very exciting. It's very exciting to see a whole thing happening just on Erlang. At least it's exciting for me as an Erlang person. Okay, so one of the earliest criticism, if you're like, okay, you got to have in your mind, there's no way, right? There's the network, you can't do it, right? It won't be fast enough. And I just remind some of you, that's exactly the arguments people were saying about the x86 Linux in the computing paradigm. And here it is, it's fast enough. And so, sure enough, our first try at this switch was not fast enough. So we put a fast version, and we'll talk more about that in this talk, but that was very, very exciting. And so I'm not going to get into this, but there's the main takeaway here is there's something in this for everybody. If you're interested in large-scale kind of data-intensive applications, if you're interested in how do you control tens of thousands of programmable switches, if you're interested in wire speed data packet processing on x86 or other microprocessor architectures, there's kind of a piece for everybody. The switch piece this is a diagram from the OpenFlow spec. So I'm not going to go into this. I thought I'd spend an hour detailing every box. No, I promise. But if you're interested in this, the LinkSwitch, the first one, is not fast, but it actually matches this architecture. So if you want to learn about OpenFlow and you are fluent in Erlang, then you can actually read the LinkSwitch and its kind of pedagogical tool. And then that may help you when you look at the LinkX switch and see how fast that is. Erlang Solutions did a great job in architecting this. I won't go into this, but essentially each one of these boxes, this is the architecture of the LinkSwitch, are libraries. They're Erlang libraries. In fact, yesterday, Mark Sugiyama here has a talk, so you can watch it on video. that goes into many of these boxes and specifically how to make a controller out of it, right? But these same libraries also go into what we call the slow path of the switch. This is very kind of nice architecture put together by Erlang Solutions. So, this is exciting, right? I mean, you can get all this stuff. But again, we were kept nagging about performance. And so, in the fall of last year, November, we ran across Maxim and his crew, and I actually invited him to come here and talk during this talk, but he couldn't make it for a variety of reasons. So I met him at the Open Networking Foundation's Plugfest this spring, where we were testing LinkX, the fast version, for the first time ever, and we compiled this video. So go ahead and roll.
Those processes to reclaim memory periodically, and we are not using garbage collection at all for certain packet processing processes.
That's right. Tell us about garbage collection again.
Hello, everybody. Let me introduce myself. I'm Maxim Kharchenko. I'm a founder of Cloudozer, the company behind Erlang on Zen. We'll be talking about a project that we did and continue doing with Infoblox. The project is called LinkX. It's the next generation of LinkSwitch. So the initial scope of this project was to, first we needed to demonstrate that our platform, Link, we call it Link, which is not to be confused with Link. This is an absolutely different thing. But you could say that Link runs on Link. So what we needed to demonstrate is that Link is compatible enough to run serious software like a LinkSwitch. Link, it's an lossless environment, so definitely it cannot replicate the Erlang OTP completely, but it is compatible enough to run LinkSwitch. From that time on, we also took on a task of making LinkSwitch run faster. First of all, we checked how the standard or the old code works on our platform, and the measures that we did, it showed that the processing delay, the time just between the moment then the packet enters the switch and until it goes out, it was about 200 microseconds. So we were specifically targeting decreasing this number. So what we did, we replaced a portion of LinkSwitch. We call this portion a fast pass. So this is the portion which really shovels packets at the high rate. And our efforts were not completely useless, so we were able to decrease the processing delay by 2 orders of magnitude. So it's now more like 1 or 2 microseconds. Yeah, but because I was going to get that thing on with me, but I decided because because I'm using serial interface, like no operating system, so it got wires and it looks like like improvised explosives. So how we did achieve that? First of all, we used the standard pattern matching of Erlang. At a glance, the Erlang looks like an absolutely ideal thing for implementation of a software switch. All this binary pattern matching thing, nobody else can do that. Nobody, almost no other programming environment can do that. But the problem is so that you can the flow tables they change dynamically. We decided to use another standard and unique feature of Erlang, which is dynamic code loading. So what we do is that then the flow tables are updated. We compile it into Erlang code and then reload the flow tables dynamically, and it just runs really fast because of that. Also, another thing you should watch, and we were trying to achieve, is avoid garbage collection at all costs. We did just that. We used the non-standard option, which suppresses garbage collection for a given process, and we restart those processes periodically to reclaim memory. In terms of processing delay and in terms of packet rate and in terms of data rate, they were all confirmed using standard, industry standard techniques. And it showed that LinkX can process about 450,000 packets per second. And for very...
On what kind of hardware?
Yeah, for these tests we were using an absolutely standard server, standard x86 server. So no special tweaks, for better network processing. Just a regular plain vanilla x86 server.
Rush down, Def Jam, we in the house.
Also, for variable size packets, we easily saturate 1 gigabit Ethernet interfaces in a full duplex mode. So there is a 2 gigabit traffic going through the switch in both directions. These numbers, they constitute 2 orders of magnitude increase in terms of data rate when compared to the old code, and it means that LinkSwitch on LinkX is kind of join a different breed of software switches where really we started to compete with the best and the fastest there on the market. To use multiple cores, you just need to spawn more instances of the virtual machine, and then you may assign, for instance, several ports to one instance and another couple of ports to another instance, and you may have linear performance increase. Then you add in more cores. These are not tested, and this is our future direction. This will require quite a bit of effort because of the coordination between these individual switches. But this will allow us to achieve even more performance-wise. So we eliminated operating system from inside the virtual machine, but we also want to eliminate the operating system when it comes to managing the hardware interfaces. We want to try to talk directly to hardware network interfaces. But this may shave another microsecond from the processing delay, and we may really get something like a next generation of a software switch, which will compete not just with the software-based things, but also with the things with hardware accelerators. But these are all probably another half a year ahead. Well, thank you very much.
All right, another half a year. You heard it right there. So, next year we should show even more. Okay, I just need the slide deck back. There we go. Okay, so if just to recap a little bit of what Maxim said very, very quickly is we now can run software switches directly, which are written in Erlang. So this is 100% Erlang, this LinkX switch, directly on Xen hypervisor, and then therefore very close to the physical hardware. And then it doesn't even use the DOM0 Linux. Today it actually does use some of the bridging, but that's future work. And this uses the Ling, which is this port of the beam to Xen. So that's quite exciting. And then to highlight a couple of things he said, which is, okay, wow. I mean, I've heard all these things about Erlang and concurrency and everything, but here is something that Erlang does better than any other system in the world that I know of that's open source, which is this pattern matching, compiling, right? And what we're doing here is this is a controller that wants to program this LinkSwitch to inspect these Ethernet packets and then do something with them, replicate them, load balance them, change them in some way, drop them on the floor, send them somewhere else, right? And in order to inspect every single packet and match against maybe 100, maybe 1,000, maybe 1,000,000 rules, right? You could have this kind of table-based approach, which is what happens in hardware switches with TCAMs and other things. But there's this amazing thing, which is if we translate, this is a remote, if there's a standard instruction set called OpenFlow, and it's translated to the Erlang structure, then the Erlang compiler can generate an optimal match engine, load it in the switch dynamically, right, and lets you process every packet while matching against some large number of rules at near wire speed. Folks, no one else can do this that I know of. No one. When you're talking about Erlang, talk about my suggestion is talk about all the great things, but highlight some of the very, very unique properties. So this is one of them. Very excited about that. Maxim mentioned the future. If you're interested in this stuff, CloudDozer has open sourced Ling. And this is all open source. And this is all open source. And I'll just say one last thing is that I'm very involved in the Open Networking Foundation, right, where they're focused on what is this right instruction set here, right, OpenFlow this instruction. And the reality is, well, clearly it's the Erlang bit syntax. That's the right instruction set for programming Ethernet matching, right? Why would you need a standard? It's there, right, with parsers and compilers and everything. So, it's pretty clear to me. Now, of course, a TCAM or hardware can't do everything that an Erlang-based switch can do, so that may limit things. There may have to be a standard subset. But, I'm trying to promote that, which is another very, very unique property of the Erlang as a language, this bit pattern matching syntax. It's amazing. Why the networking community hasn't picked up on that sooner, I have no idea. If you do, let me know. I suspect it's structural. Okay, so I have to blaze along here. So let's put it all together, right? Today, the state of the art in distributed platforms is not the state of the art. It can be a bit depressing in terms of how much force is needed to stand up a very large, say, Hadoop cluster. It's possible. The question is, how easy is it? But so one way to think about it is today, there's certainly these pretty amazing platforms like Hadoop, Apache Spark. You can imagine SensorNet applications. But there's so much stuff in the middle layer today. So many layers of complexity and abstraction and knowledge and very specific ways of looking at the abstractions. It's the complexity of this red layer can easily overwhelm the value of the application. From an operational OpEx perspective, from a programming perspective, all this complexity. But there's hope. Because not unlike when virtualization happened on the computing industry, there are these fundamental foundational abstractions which are absolutely ubiquitous. Right? The microprocessors today are essentially ubiquitous, and the various hypervisors make an abstraction that's like Zen. Right? There's only a few that is, means that abstraction is ubiquitous. The Ethernet frame is ubiquitous. So whether the network from a layer 2 perspective is 4G or Wi-Fi or even InfiniBand or whatever, from a software perspective, most software stacks fully recognize the Ethernet frame, and it's very well documented and easy to think about. And if you are familiar with the Erlang bit pattern matching, then it's easy to actually write parsing for the Ethernet frame. So we have these very, very ubiquitous fundamental abstractions, and that is new. The fact that these fundamental abstractions are everywhere in the world, already installed, they're already there, is something that's new in 2014 and wasn't true in 2005 or 1995. So one way to think about it is this is a very, very special time in computing. If you ever felt a little bit jealous that you weren't there, like during the PC revolution, right, where, because the computing industry in the 70s was extremely kind of stable, right? And there was this very, very exciting thing that some of us only read about, how that transformed. That's the kind of situation we're in today. Absolutely at the brink of a new frontier in computing, based on the fact that there is this ubiquitous Ethernet and multi-core kind of architecture already installed in the world, and there are visionaries. If we look back in time, this is a picture of a guy named John Gage, who very prophetically stated that the network is the computer. And so now we're at a time that the world has problems for this machine, and is now searching and seeking for system-level and programming-level solutions for this machine that's already installed out there. And that's why I'm here, and that's why I would guess that Richard's here, and other of you are here. There is this magnetism to this community because it's possible, by no means guaranteed, but it is possible that this community could very uniquely, because of the head start and the kinds of things I said, solve many of the problems going forward. So one way to think about it is we just need a better distributed system, right? If all the talks that I went to yesterday and the ones I see today touch on these major themes, if we could make specific distributed apps, if we had scalable analytic libraries, if we had scalable system abstractions, not the red thing I showed, but things like software-defined networking, things like graph databases, functional languages, all the things that allow us to really build these blue systems at scale, all based on this very solid foundation. It seems now, for the first time ever, in my opinion, having looked at distributed systems now and being focused on them my entire 20-year career, this is the first time that many of these problems seem actually tractable at scale. That mainstream applications can be distributed and data-intensive in general. And I would state that this is absolutely not a theory, in the sense that we've started to really make proof of concepts and prototypes around this with what we've done with Tapestry, OpenFlow, Zen. It's just the beginning. I'm not making any claims. The idea is hopefully to interest some segment of this community to really push this farther and see how far we can get. Okay, so that's great. Sounds fun. But really, Stu, That's a lot of work. It's going to require a lot of brain power. It's a big, big, big project. What's the app? What's the real app, right? And I think that is another exciting thing about the time we're in. What I'm describing to you is the need that the world seems to have and a growing number of distributed applications, right, that are underserved by technology. That's the opportunity. But no one really knows what they are. And that's exactly the situation of the PC in, say, the mid to late 70s, right? It was very clear there was something fundamental going on, but you couldn't really predict that it was going to be the word processor that was the killer first app, right? And it was. IDC in 1976 has a report that the dedicated word processor market, of which there were like 30 companies making dedicated word processors, was going to go from a $600 million market to a $1.2 billion market by 1981. It never happened. The PC absolutely changed that. So we're at that kind of thing, but nobody knows. I think that success stories like WhatsApp have really started to bring attention to the Erlang community in a very, very positive way, right? And I hope this community can leverage off that because I think that's great. Okay, so I'm not going to get into, I don't think I have all the time, too much of this. So we spent a lot of time on kind of system level stuff. Okay, if you're into system stuff, and I'm guessing some number of you are into that system stuff, that's great. But I'm guessing some other of you are into more computational things or higher level things, right? And so I'll go into a little bit what Tapestry is and how, again, this community is so amazingly positioned. Tapestry is a network complexity analyzer. I'm not going to go into all the foundations. You can read the paper. But essentially what it does is it tries to capture with one number how complex a whole organization's network is in a meaningful, quantifiable way. Now, by network, we don't mean the jumbles of wires and boxes and stuff. We mean the number of endpoints that are interacting, right? The logical network, this highly dynamic logical network of connectivity. What business processes are actually, or organizational processes are actually interconnected and riding. And one way to think... Yeah, yes, you're right. Okay, I'll fix that. Yeah, and it converges to 42. So it's on its way. You see it's red? It's on its way. It's a convergence problem. So so the amazing, so what does it do? So it actually is a big data problem. That's the point of this. So if you're interested in big data problems, inside of Tapestry, we have to find communities of things automatically, right? That happened to me on my old job. I was a technical lead for the National Center for Data Mining for 6 years before I started Infoblox. So, it's fun to get back to that kind of thing. It's very, very interesting. And Erlang is very, very well suited for algorithms in this area. And it's an endpoint metadata problem. I won't go into all these slides, but essentially we're extracting from the network because now we have a wire speed processor in the network, right? We can do any kind of pattern matching we want. So we can extract from the network metadata like where various endpoints are trying to go based on just looking at DNS traffic, for instance. So the domain name service is this kind of signaling protocol in networking, and with Tapestry, we can, with the OpenFlow switch, we can actually grab that telemetry data, and then we know these triples, like, okay, this IP address is trying to go to this IP address at this time. So this is just like triples, time, IP address, IP address. And you can just imagine so much metadata that you might want to do for something that's very useful. And then this metadata has to be organized, so it's kind of like, in this particular case, like a call record. So if you don't know what the endpoints are saying to each other, but you know who's talking to who, right? That's actually looking at DNS telemetry data. You can do that. And then you feed that into a machine, which does this magic thing because everything looks like a graph, right? A graph in the mathematical sense, like, oh, these pretty pictures. And then you feed that in this machine, and then you do an automatic algorithm called community detection. We picked one. It's called label propagation, which came out of the physics community, right? That's open source, written in Erlang. It's like I wrote the first version, so, that's a testament to Erlang, right? There was a pretty easy algorithm to read in the paper, and I was able to pretty easily translate it because of the functional programming language aspect of Erlang. And, I'm a really terrible programmer. So, Erlang is not just for the experts. It's for the people who have this problem and actually have a less impedance mismatch between the programming language and something like a mathematical formula, which was just great. And if you're interested in that stuff, this is a whole, community detection is a whole field in of itself. So if there are any machine learning community detection people out there, we'd love to see, 20 other algorithms installed in Tapestry so we can pick and choose and decide which one is the right one. Erlang is a great way to do that. And we could even dynamically load a new algorithm at runtime in a Tapestry instance, which you can't do in very many other examples as well. And then what does it actually do? So this is for more of the analytics set. It just finds communities. This is like a invert, like kind of upside, kind of sideways like this histogram. It just finds all the communities. Like here's an activity of endpoints. Maybe that's a big, like that's everybody going to Google, and then that's everyone going to Facebook, and then like that's a Hadoop cluster, and that's like 3 people experimenting with like RabbitMQ, and something like that, right? And you just order these. This is the output of the community detection. And then you just order these by size. So this is like, this had, this is Google, so it's like everyone we looked at in the network. So it's like, 10,000. And then this was Facebook, that was like 5,000. This was like 3. So you just order these by size. And then this is not a daunting formula, actually. To Katie's point yesterday, it just very easily says, well, if this is the index J, so this is activity 1, blah, 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 that's J. And x of j is just the size, right? So it's this value here. This just says find the max j where x of j is greater than or equal to j. So you just walk up this stack and you say if it's an 8, that means there are at least 8 big activities that are bigger than 8, but there's not 9 activities bigger than 9, right? So it's the balance point. This is kind of a cool kind of property for large things. You can see it has this kind of, it's statistically robust. It kind of filters out these big things, and like if you had a million little things or something that was a million, it would be filtered out. So that's like one example of a kind of property that you can compute on some very large network. Okay, I'm guessing as we together go through a journey of making very large distributed systems, we'll want to compute lots of properties like this. I'm not claiming this property is particularly useful. We think it is for certain applications, but this kind of computation, I think, will be extremely useful for distributed system designers over time. It's definitely a widely distributed problem. Some of our customers, large enterprise retailers, have over 15,000 recursive DNS servers, right? And a DNS server is the thing that your laptop or iPad or whatever contacts before it goes and talks to Google to find out the IP address that Google goes. And if you don't gather to the telemetry at the recursive layer, you lose the endpoint data, because the way DNS is structured, if you try to just capture DNS traffic at the egress point to the internet, then it would just show these DNS servers. It wouldn't show the endpoints, right? So to just get this data, you got to go way out into the network everywhere, right? But that's easy to do now, because if this is a recursive DNS server somewhere in Timbuktu, or where's that place Richard Feynman was always trying to get to? Anyways, someone will know in this audience. Then you can put a little just x86 box right in front of it, and it'd be fully controlled through the remote control protocol like OpenFlow, and you can look at all the packets and gather telemetry, and then send it back to some data center somewhere that's doing this big data computation, right? So this is a very wide area telemetry application, all using the same stack, all using that same stack. And one of you, why does Stu have all these creepy, weird pictures, right? Like, they're not nice engineering diagrams that we normally think. Well, one of the reasons is, and this is an example, kind of a blown up example, like here's a data center in the background that has like a bunch of machines computing Tapestry and running the Loom code. Here's a LinkSwitch that Maxim described. Here's some DNS recursive server. Here's some routing services that are legacy, because you should be able to intermix with those easily, right? The point here is that it's all logical, right? So the complexity of network systems in themselves become mind-blowing very, very quickly. So the kind of way to think about nicely organized network is done. You can't do this anymore. But again, this community has been dealing with very complex logical structures for a long time, is perfectly suited for that. So again, a unique opportunity. So, coming to the end. Look, if you can buy network gear, and it's the same stuff inside, except it has a lot more interfaces, or could have wireless interfaces or 4G or whatever, could have fiber, whatever, but it's the same stuff inside, CPUs, not ASICs, not NPUs, but CPUs, same stuff as the servers, right? Then really, really, we do have a new machine, right? This picture of John Gage again. And I think we're going past the cloud now. This is a new era of distributed computing that we're entering. And Erlang and the OTP are absolutely, I think, demonstrably now, I'm not claiming victory, but we hope that we've just touched enough of the pieces with real code that you can actually touch and use. It's demonstrable that Erlang is very specially suited in this new world. And you should explore it on your own, right? This is a little Intel Atom 4-port server, right? Just an Intel Atom server running Zen. You can actually run Zen on it. Running LinkX, so you can run LinkX on it. I just bought it from portwell.com. They have a whole host of x86 and other things that have lots of network interfaces on them. These kind of things they call communication appliances, but they're just x86 boxes with Ethernet. And the Ethernet just, appears to the links. So you can buy this. This was cost me about $300 like a year ago. The price is dropping. And then one of these wires goes to my entire internet at home, like my internal network at home, which I have 3 kids, like 12, 8, and 4. They watch a lot of like Netflix and Amazon all the time. And one goes to the internet connection. So it's inspecting at every single Ethernet packet and matching that against like 100 OpenFlow rules, right, in real time. And I was so confident this would work. This is an Intel Atom. I put it in like 3.5 weeks ago, and I went on a week-and-a-half business trip. Wow, I was sweating it. I really was, because there was no way like for me to easily, reboot it or tell the family how to fix it. And I thought, oh man, if this thing goes out, I am really sunk. And I'll tell you, it didn't. It worked like a champ. I came home. When the kids got out of school, however, on this platform, their friends came over, and the amount of streaming video in my house went up, right? And this thing started to choke then. So, but the solution is you just put a bigger processor in there, right? So now we can think about networking problems in the same way we think about computing problems. We don't have to change the software in this case. We just put a better processor in there, which is great. So I encourage you to look at that closely. Okay, very quickly, I think I have like a minute left. For the theorists, so I've kind of talked about applications people, for the systems people, for the theorists, look, this is your time to shine, right? There's so many abstractions that we have to think, and not only the theorists, but the kind of language people, for example, right? Language design people. What are we going to do? We got to fix this, right? For the theorists, right? The Haskell people claim I/O is a side effect. Is that true, right? I don't know. You tell me. Maybe communication is somehow fundamental, right? We don't have any theory for this. So those of you academicians out there, let's go attack, I strongly suggest you attack this problem. Maybe Joe's contract checkers are important. I don't understand them well enough to know yet, right? But this is the kind of thing that we should explore together. So here are some grand challenges, right? If Erlang is going to step forward into its natural right into distributed systems, as a community, we need to attack these problems. I won't go through all of them, everything from security to, if I have a million match rules, I need to now compile those. So we need to add more scalable things and, think about different ways to deal with the mailbox and things like that. Packaging and code, come on, can someone just find out whoever wrote Maven and bring them over here, do it? They're just things that have to be done. And I'm guessing, just looking in this room, right? Everyone, it's a distributed problem, right? If one of these, this is like GUI, not like I'm going to make a web page, but like how do I actually visualize a system with a million things in it, right? In some meaningful way, the diagnostic tools. So pick your choice, whatever is your passion, but we need to collectively do that. I propose, hey, next year, let's this conference have a 100% Erlang-based network, right? Right here, right? Let's do it, right? So that all of your packets are being processed by Erlang as they go out to the internet. And we can have a hackathon. Bring all your weird Internet of Things stuff, and we'll see what we can do, right? Let's do that. We can do that in a year. So let's make it happen. So in closing, I just want to say, one other thing with the theorist. If you don't know this is a book called The Connection Machine, which is a 1985 ACM Distinguished Dissertation for Danny Hillis, who went on to build the Thinking Machines Corporation and make the Connection Machines series. If you're brand new to all this stuff, right, this is a great actually entry point. Again, we're at a really special time where widely distributed computing with programmable networks is now mainstream. You don't need $1 million, $2 million, $5 million to build a machine like this. You can build a machine with a few $1,000s, but some of the fundamental research was done a long time ago, just like in object-oriented programming and other things. So go do some research. It's fun stuff. Okay, so I'm between you and break. I want to thank you, but I need to do one more thing. Can we take these lights down and the high lights up? I have this problem. I live in San Jose, in Silicon Valley. It's hard to bump into Erlang people in general. Like, statistically, if I just go, I can't find any. So my wife is always, I'm like, I'm going to see like 400 Erlang developers. She's like, no, that doesn't exist. So I need to take a picture of you guys. I'll take a video. And then if you could all stand up, that would be helpful. And then, just like Katie said, just like look really friendly, like maybe, like really friendly, and then wave, and just say, maybe on the count of 3, just say, Erlang. 1, 2, 3. Erlang. Oh, come on, you can do better than that. Come on. We're at the brink of a whole movement here, okay? Really loud this time, okay? Ready? 1, 2, 3. Yes. All right. Thank you very much. Have a great conference.